All right. Angled launch. So you watch the video this time of a home run, which is hit something like this. I think it actually was a little bit more of a hit that went out something like this, hit a piece of the stadium, sort of bounced back like this. But that time is not too different than if it would have just continued to hit the ground. But anyway, it followed this nice smooth parabola, more or less. Let's go over those questions real quick. So the first one was the time total. Most of you got something around 5.5 seconds. Somebody put something much longer than that. They might have included the pitch, or I don't know what, but somewhere around 5.5 is reasonable. All right. Was the time more or less? So the time for the home run was actually less than the time for the pop-up. It might have surprised you. That would surprise me the first time I saw that, at least. But yeah, there's a definite reason for that. It has to do with which way you're hitting it and when a flight stops. Okay, was the ball in true free fall? No. There's air. In fact, at no point was it in free fall, particularly because even at the peak, it was still moving forward. So even up here, it was still moving forward. There was always air resistance. Maybe the instant it hit the spot here, it came off. It was still even moving then. So, no. Okay. How long did the ball take to get to the peak? Well, if it does follow this symmetric path, then the time to the peak should be 1/2 the time total. So it should be, if you got 5.5 seconds, it should be somewhere around 2.75 seconds. All right. How fast was the ball going in the upward direction after it was hit? Let me just be clear here. When this ball is hit, here's the bat, here's the ball heads off in this direction. If you were to describe this in 2 words, you'd say the ball is being hit both forward and up. And the combination of those two gives you this diagonal. So we're not so concerned about the forward direction. We are concerned about the upward direction for this, because that's the math we know how to deal with already. So how fast is it going the upward direction? Well, this is actually the same as yesterday. If it took 2.75 seconds to get to the peak, well then you know, we can actually do this for the way up or the way down being easier. That means t from the peak to the end is also 2.75 seconds. So go from the peak of the problem and just look at the vertical direction. On the way down, it's like this. So there's the peak. Then here is 1 second later. It's going 10 meters per second. You remember this? After 2 seconds, it's going 20 meters per second. And after 3 would be down here, but we're not quite to 3. We're at like 2.75 seconds. That'll be 27.5 meters per second. Of course, your numbers will match your peak time, not this peak time right here. That will adjust. All right, so that speed of launch upward is about, we put a little about, 27.5 meters per second. And then, of course, as you convert that to miles per hour, 27.5 meters per second, go to miles per hour. You can do that multiplication like we did yesterday, times 2.24, or you could even do the 22s. So over here, it's at 22 miles per hour. 2 seconds, it's at 44. At 3 seconds, it would be 66, but didn't quite get there. It was 3/4 of the way to it. So if you take your 22 and roughly break it up, well, you can break it into quarters. You get 5.5 each. So this one comes out to about 60.5 miles per hour. So you're going to get somewhere around 61 miles per hour. Okay. Now, some of you may say, wait a minute. I know something about baseball. No home run is hit at 61 miles per hour. You're right. The 61 is only the upward piece. There's also a forward piece that's very fast. You got to combine those two to get the actual ball speed after it hits the bat. All right, if there were no air resistance, it would reach, actually, this pathway would turn into this pathway. It would go higher and farther. You can look stuff up like this. And then, it would not go to the moon, however. How high did the ball go in meters? Well, that's that peak distance. And we had this equation, VIT plus 1/2 AT squared. Oh, I'm off the chart. There we go, sorry. Higher and farther, D peak, VIT plus 1/2 AT squared. And the easier way to do this was on the way down, because on the way down, the VI is actually the velocity at the peak, and we're only doing this for the vertical direction. This actually works, it's amazing. But that was 0. So then we plug this in. D peak is 0 times 2.75 plus 1/2, still that 10 times 2.75 seconds squared. That D peak comes out to 5 times 2.75 seconds squared, which is, I'll go run that in my calculator real quick. 2.75 times 2.75 times 5 is about 37.8, which is about 38 meters peak height. Now, if you remember from yesterday, the peak height was different than this. It was actually higher. And that has to do with this launch speed, this vertical starting speed, this one right here. The faster you hit it vertically, the more time it spends in the air. That doesn't mean the farther it'll go home run wise, but the higher it'll go and the more time it'll spend in the air. All right.